Done. Let's go to 91. A car moves uniformly along a horizontal sine curve. Wait, what? A horizontal? What does that even mean? Y is equal to a sine of x upon alpha. Okay, I understand it's a sine curve, but horizontal. Oh, okay. So it's yeah, it's just on the ground. It's flat. That's what they say. Where a and alpha are certain constants. The coefficient of friction between the wheels and the road is k. At what velocity will the car ride without sliding? So car rides without. Okay, fine. Understanding what's happening. So, oh, this is really bad. And it's at what? Constant velocity. Oof. Huh. All right. So it moves constant velocity. Fine. This is bad. It's like this is the sine curve, and the car is moving on it. Okay. And when can it slide the most? So at each point, there's only friction acting on it that can balance it. And yeah, right. So it's position. We just need to get the acceleration somehow, right? Wow, this is going to be really bad. Oof. So, how do we do it? Like, okay, think about it. You got a sine curve, which looks, I don't know, something like that, right? Okay, now what we want to figure out is, in let's say t seconds, what will be the displacement from the start? Like, what will be its position after t seconds? That's the main thing that we want to figure out. So for that, first of all, we'll have to figure out this path length for any value of x or y, or yeah, basically like that. So, oh, this is going to be really hard. How am I going to do it? uh right, what do you actually want? We just want the acceleration, and acceleration will basically be like the position of this like r vector, of course, that thing upon dt, but the derivative of that, right? So actually we don't actually need to know what your r vector is. Okay, this is awful. Only thing you know is that the tangential speed is constant. That's it. I mean, the speed is constant. It's moving on this path. Uh, yeah, it's almost as if you know nothing about it. How do we figure this out? Other than, of course, integrating and finding out what this path actually is. So, dr upon dt at different locations, it has different velocities, of course. Hey, yeah, I mean, that's actually, but the time derivative of that thing, huh? Oof, the acceleration. Uh, oh God. Yeah, I mean, like, we know the position. We also know what the velocity actually is. It's just this thing, right? So we know the velocity vector dependent on x and y. Yes, we know that. But we don't know how x and y change with time, right? Or do we? Maybe we know actually. We can write differential equations for this, right? Not exactly x and r, but let's say x and theta. No, x and y are the best thing to do this, right? So fine, let's think about it. You got a point like this. This is its x y coordinates are like x and y, and this is going with theta like this. So at velocity v, of course, so then you just have v cosine theta is equal to dx upon dt. Then v sine theta is equal to dy upon dt. So like, of course, dividing that, just get tan theta equal to d. Okay, I understand that. No problem. What we would like is that, sorry, dy upon dt. But yeah, we will just look for x and not for y. That's what we want to do. I think that would be the good thing. Or in fact, let's not even worry about this. All we need is just the acceleration. So first of all, the velocity as a vector is just v cosine theta and v sine theta. We know that. So its time derivative, that will be like v and wow, this is weird. So it's going to be negative sine theta and then d. So definition of this thing is just cosine theta, and then d theta upon dt. So we don't know what d theta upon dt is, do we? Yeah, we don't. Oof, we don't know. Also, this v doesn't change. Really, we just need to figure out what this quantity is. D theta upon dt at that particular point. So what will theta be? How does theta change with time? This is a very, very weird question. Like, okay, divide this again time, that should divide upon dx. Cool. Not really doing it, you know. Hmm. Oh, we could use this expression, right? Y is equal to a sine of x upon a. We haven't used that till now, have we? No. So we can use that. So instead of writing this, we'll just write, oh yeah, so we can do it, of course. You just know that tan theta is equal to, so yeah, perfect. You can write tan theta in terms of x completely, right? So just the differentiation of this thing. So it's going to be what, a upon alpha sine of x upon alpha, sorry, cosine of x upon alpha. Cool. And then since we need this thing deta upon dt, what we should do is yeah, right, why not just do that thing? Isn't that correct? Of course. So deta upon dt is not exactly what we are looking for. Maybe we are looking for secant squared deta upon dt. Okay, this is getting bad. Fine, let's try it out. So this really is just deta upon dt is equal to cosine squared theta times a upon alpha negative sine of, oh come on, it's got to do with dx upon d theta, sorry, dx upon dt, and that certainly has to do with theta over there. Oh hey, okay, we know what to do. We know what to do. Because as a matter of fact, you can use this, and instead of using theta in terms of x, we'll use x in terms of theta. Why not do that, huh? Exactly. We could definitely do it. Now, how is a different question, but let's try it out. So cosine of x upon a, man, x upon alpha. But still, like dx upon dt, how am I going to figure that out? It would have been so much better if somehow we got, okay, this is just, we can't dream, right? That won't work. And what do we actually look for? The coefficient friction between the, yeah, so like at what velocity will the car ride without sliding? Fine. So for that, you have to figure out the acceleration, actually the maximum acceleration. That's what we have to figure out. So whenever your d theta upon dt will be the maximum, right, at that point, and your, yeah, like you're, okay, I understand that. And wow, this is bad, really bad. Sure, you can write x in terms of theta, but okay, it's like cosine of x upon a. Okay, this won't work. This just won't work. Because as a matter of fact, theta is in negative pi by 2 to pi by 2. So this is really usable. But x, sorry, theta is in negative pi by 2. So it has limited range. But x, it goes from 0 to infinity. So it has a bigger range. So I think it's better to just use x. I really want to get rid of this x so that I can just not worry about right, what if I wrote everything because of x? What would happen in that case? I have no idea. Let's try it out. Let's write it in terms of x completely. So we'll differentiate this, and then that will just give us theta upon dt is equal to secant square. It's like, okay, cosine square theta. And then, oh, what is this? So you will have to write everything in terms of tan theta somehow. Okay, we'll try to figure that out. Fine. Sorry. This is our acceleration, yes? Hey, wait. This the magnitude of this acceleration, that is actually just v theta upon dt, right? So all we care about is when d theta upon dt is maximum. Fine. So then, yeah, sure. We can try doing it. So first of all, secant square theta, that's just tan square theta plus 1. And guess what's tan theta? Okay, we can do it later on. So 1 upon secant square is like 1 upon 1 plus tan square theta. And derivative of this thing is a upon alpha squared, and we got negative sine of x upon alpha, all that stuff. And then you got dx upon dt, right? Mm-hmm. It's still not helping. Because dx upon dt is also like variable, not helping, right? It's not helping. So then what do we do with it? Dx upon dt. Slope changing drastically. When does that happen? Okay. You will have to figure out what this whole curve path length is. Otherwise, it's not doable, I think. Can you just do theta upon dt like that? No, it's dependent on x and whatnot. It won't work like that. Moreover, dx upon dt is something we don't know. What do we know? What do we know? Okay, it's like these two equations are things we know. Yes, fine. But these are not helping. B cosine theta is equal to dx. Oh wait. Did I just say this? Of course. Sorry. It's doable. It's just very doable, in fact. Really sorry. Yes, it's wow. Sure. It is doable. Really is. Alright, so you got dx upon dt, you can write this as b cosine theta, and then you got all of these things, and then you can change everything in completely in x. Yes, and it will be nice. And cosine theta as well, I think we can change it in x completely, right? You got tan theta, so cosine theta is not that huge a deal, I think. First of all, what's this? It's just secant square theta. So sorry, it's cosine square theta. Sorry. Then you got this stuff. Then what's dx upon dt? So dx upon dt is just v cosine theta. So now it just becomes cosine cube theta a upon alpha squared, and then you got this thing. So v, and we are looking for magnitude anyway, so we'll just say sine of x upon alpha. Cool. Now cosine cube theta, we need to write that in terms of x somehow. So you got this expression. Sine of, what about we write sine of x upon alpha in terms of theta? No, it's still just both of them are equally horrible. Okay, so now what we need to figure out is when will this be maximum? Oof. Yeah, so like just think about it. Cosine cube theta sine of x upon alpha, when will this be maximum? So think about it as a function of x, right? So its derivative of x must be 0. So let's figure out how that will be. It's like 3 cosine square theta, right? Sorry, and then negative sine theta. So negative sine theta, then sine of x upon alpha, and then you got d theta upon dx, which, okay, d theta upon dx, you say. It's not helping. Okay, cool. Or maybe just do it in terms of theta, right? We could maximize in terms of theta, because theta goes, wait, the maximum slope of this guy is actually just pi upon 4, not pi upon 2. So maybe x is the better option, really. And this thing, okay, you got this over here, and then plus derivative of this quantity. So it's going to be plus cosine of all that's like 1 upon alpha cosine of x upon alpha. This has to be 0. Now, when does this happen? When is it equal to 0? One thing that I think it will happen when this whole thing is gone, right? Whenever say cosine of x upon alpha is gone, that will make this happen, right? Because then at that point sine tan theta will be 0 as well. That means sine theta is 0, cosine square theta is not 0, and then d theta upon dx, what could it be at max? Like that's cosine square and then a upon it, yeah, all that stuff. Hey, actually it's not that bad. So it's like cosine power 4 and then some some stuff related to this functions, like the derivative of that function, right? Cool. Net, yeah, you understand that, right? So it's clear that this does become 0 when x is equal to pi by 2 alpha, or in fact any odd multiple of pi by 2 times alpha, right? And I guess that will be the maximum. Because so what happens when I put that into this, where it go, this quantity? So then this will be 1, and cosine cube theta, well, tan theta is 0, so cosine cube theta will be 1 as well automatically. So it just becomes AB upon alpha square, which is to be expected because look, cosine and sine, these have maximum as 1. So I should have already guessed that maybe it can happen that both will be 1. But yeah, technically as well, this will be the maximum acceleration. And once we have this, we can figure out what the maximum friction will be. So it will just be mass times that. So MAV upon alpha squared. That's the maximum friction. It should be less than or equal to K times mg for this to be continuing. Perfect. Finally. So you can cancel these away and we just have K bigger than or equal to. That's what we need to do, right? No, we want at what velocity? So V is less than or equal to kg alpha squared upon A. This was just a really big question with a lot of calculation, but not really all that different from what we do. So there we go. This is the maximum. I'll write it as a condition. So B less than or equal to kg alpha squared upon A, right? Okay, 92. '92 is a chain of mass m forming a circle of radius r is slipped on a smooth round cone with half angle theta. So do we not have figure? Find the tension of the chain if it rotates with constant angular velocity omega about the vertical axis coinciding with the symmetry axis of the cone. Slipped on, okay, so it's like it's put on this cone. So this is the chain, for example, like this. That's what you're saying. Hey, so we already saw this kind of question once, didn't we? Right. Oh yeah. Fine. So how do we do it? You know what? I think the surface tension thing might work. No. Elemental analysis is the best. So when I said surface tension, but I meant what we do in surface tension. I mean problems. Yes, that is we just split this in half and then yeah, right. It's gonna be very complicated because then this force is like this everywhere and yeah, no thanks. Instead, we want to do analysis of each element individually. So first of all, what will our element look like? It will be some kind of arc. So it's a very small arc. So if like maybe this angle is d theta and the arc, the subtensis angle is what we are looking for. Now this radius is r, this will be r d theta. You got the length and everything. This thing is tension T is pulling it in these directions. So then you can say, okay, this is like, yeah, I'll draw it in a better way. So maybe you will understand T and T over here. And this is how the arc is. And then you got theta angle. So if this was finite, that is, this would be the thing. So like this is theta angle. So this will be theta upon 2 angle. Right, you got T over here. What is the tension? What's the force that's pushing it inside? So this angle is just 90 minus that, right? Yes. So this will be pi by 2 minus theta upon 2. So cosine of that is like sine of theta upon 2. Isn't that right? So basically it will be 2 sine of theta upon 2 times tension. That's the force pushing it in this direction. But the thing is that, yeah, well, oh, I think I messed up somewhere. Right, this is what sine of this angle is, and cosine of this angle is like that. So yes, it is actually correct. So this, for small angles, it will be the same thing as theta times t. So for small angles, this whole thing, this whole section, it feels a force of t d theta, right? Now let's take another view of this thing. So this is the same thing. It's that element, right? You got the normal force acting on it. So because it's on this kind of surface, normal force is acting like this. It's making some angle with it. So this angle, half angle, was alpha. 9 minus alpha. You got alpha over here. This is normal force. So you have n cosine alpha is what's pushing it out, and this tension pushing it in. So you can write, okay, t d theta is equal to, so whatever normal force is on this thing, and then n cosine of alpha and whatever. So yeah, I'm writing capital N, but this is actually supposed to be an infinitesimal quantity, because this is so small, it has to be an infinitesimal quantity. And similarly, okay, and what about the vertical balance? So you got gravity acting on it, it's like it's dmg, and then you got normal over there. That's gonna be n sine alpha, and then you got dmg. So divide this, and you'll just get, yeah, t d theta upon g dm is equal to cot alpha, right? So write it a little better. Tan alpha is equal to t upon g, and then dm upon d theta. So m will just be, wait, did this tell us the mass and length? Yes, 92, right? Yes, so a chain of mass small m and radius capital R. So what will dm be equal to? Dm will just be d theta upon 2 pi. So that's the fraction of the ring, right? And this times small m, that should do it. Yeah, so this will just be m upon 2 pi, where t is of course the tension. Okay, wait, I think we messed up. I didn't read this part. Find tension in the chain if it rotates with a constant angular velocity omega. Oh, oh yeah, so like there's also the centripetal force acting on it and whatnot. So this is not d theta anymore, right? So instead it's like, so it's dm upon, oof, we have to write these different equations differently. So this is in this direction, that's in that direction, and then plus, so we call centrifugal force, right? This is r, yeah, it's rotating with r over there, I think so. Then you can say it's just it's just the omega squared r, that is the acceleration. So the force on this is just dm omega squared r. Yeah, so then put that in there, just d d theta minus dm omega squared. Write these equations actually a better way. It's getting very good. Fine. What do we have? d d theta minus dm omega squared r upon gdm, that is equal to 1 upon tan alpha. So basically tan alpha is equal to, or maybe in fact just leave it like that, I don't know. Yeah, just leave it like that. So this will be like t upon g, and then d theta upon t upon dm. What will that be? We already got that dm is just theta upon d theta upon 2 pi times small m, right? So this will be 2 pi upon small m, and then minus omega squared r upon g is equal to basically cot alpha. This should do it, I guess. So from here we can figure out what was this that we wanted to figure out. Find the tension, of course. So 2 pi t upon mg is equal to cot alpha plus omega squared r upon g. So we just have 2 pi t is equal to mg as that. So oof, mg cot alpha plus m omega squared r. I should do it. So tension is just 1 upon 2 pi into, so I should say m upon 2 pi, right? M upon 2 pi into g cot alpha plus omega squared r. Weird, isn't it? So this is it. That's what we needed to know. Awesome. In fact, like this is so general that we can keep it as a, I mean, formula kind of thing, whatever. 93. It's a nice question. Yeah. A fixed pulley carries a weightless thread with masses m1 and m2 at its end. There is friction between the thread and the pulleys. This pulley carries a weightless thread with masses m1 and m2 at its end. Okay, it's like this. Fine. Friction between the thread and the pulley. Oh, the pulley is not. Ooh. Okay, this is different. So the pulley will be rotating, right? And if its mass is really small, then it pulleys inertia is 0, and then it will, like, there will be no work done by the friction in that case. Without knowing the pulley's mass or anything, it's kind of hard to do it. Because the thread starts slipping when this ratio is slipping. But you know what? Oh wait, it's a fixed pulley. Okay, does not even make a difference. Pulley, so it should be rotating, right? What if it's not rotating? What if the pulley is just made to be very smooth such that we can, right? What if it's not a rotating pulley in the first place? Generally it is, but what if it's not? In that case, we can solve this. But if it is rotating, don't we need the inertia of the pulley to do anything? Yeah, I guess we do. Okay. Ah, fine. So we'll just assume that the pulley is not rotating. So yeah, then we can do it. First of all, what is the normal force on this little section? Uh, so for we already got that for each of these small arcs, the force that's pushing it inside is t d theta. So that's our normal force basically, right? So the friction will, so if it's the critical condition, then the friction will be this times the coefficient of friction. So you can just integrate it over this arc, this finite arc, and you will just get t times the theta of this arc, which is basically just pi. Oh wow, this is what is this? Yeah. So t times pi. Why is this so? How does pi jump out of nowhere? But it really is like that, because if it's cylindrical, then it has to be like that, huh? Uh wow. Just wow. Fine. So t times pi times k. That is, so yeah. The thing is, like, the friction is changing everywhere, doesn't it change? Yes. Oh, okay, then this is maybe not how it should have been. Okay, think. If it's stationary, then we can say this thing. So the friction acting on this guy, it will change slightly, right? Yeah, it will change slightly. So what do we do when we integrate this thing? Oh no, this is wrong. This is really wrong because when we integrate, we are not taking into account. Oh, okay, yeah, this is just really bad. What really is happening is that you have some tension force over here, some other tension force over here, I think. Right? We don't even know what. Uh, oh, this is really. So for equilibrium, we just have M1G tension in this whole wire and M2G this whole wire. So these tensions are different. That's the main thing. So we need to figure out how this changes. Yeah. Mm-hmm. We definitely got what's the force applied towards the radius. Yes. But the thing is that will be cancelled out by the normal force anyway. We need to figure out what's the tangential force on each of these elements. So you got T in this direction and then so T plus dt in this direction and T in this direction. So it's almost as if it's like horizontal. I know it's not, but yeah, cosine, theta, and all that stuff. So that approach is one anyway. So it's basically just dt, right? So dt is the force on this in the tangential direction. So you can say okay, dt is equal to df, where okay, no, write df in a proper form. Uh, it will be k times the norm. Oh yeah, I understand what's happening. It's k times the normal force, isn't it? Wait, no. Uh, it's not always just that. It's less than or equal to this thing, yes, but not all of the times. No. Uh, Come on, think about it. What am I doing? What am I doing? This is force acting. You can't just say it's gonna be k times of this thing. No, because dt is different for all of these, right? And then t is different, and it should change such. Uh, so what happens if one element of this thing uh, is not being held by friction, right? The friction is not sufficient for that one element, but for the other elements it is. That would suggest that this element would just start going on and others won't. So that's kind of wrong, right? So in fact, it has to be that all of the elements are going together. So that would mean that all of these are at critical condition. Is this correct? Is this a correct thinking that all of these are at the critical condition? I guess so. Like what if one of them has friction that is, oh yeah, so if one of them has friction that is not sufficient, the other thing has to be done by the tension force, right? So your dt will basically be adjusted such that this will happen, such that yeah, and the friction has to be at critical condition in all of these cases. That would be like that. Yes, so friction has to be in the critical condition at everywhere. Seems counterintuitive at points. Okay, fine. Just go with that then. This is wrong. Yeah. So what do you have? dt is equal to k times of d theta. Sorry, t d theta. So that would be natural log of t as it goes from t1 to t2 is equal to. So what is this d theta really? It's fine. We'll just say it's that times theta, of course. So this will be friction coefficient times theta, where theta is the change in the angle from wherever you start measuring the angle. That is, maybe we start from here or over here, whatever. This change in angle is what we are looking for, which is basically in this case pi. So pi does show up in this case. Now this is natural log of t2 upon t1. So t2 is just m2g for stasis. Now this will be m2 upon m1 is equal to pi times of k. Good. Makes perfect sense, right? And then when m2 will become more than m1, right? Sorry. When it will become more than some a specific value, right? It will start going. So this is the critical condition. So actually what is the condition for stasis? It will be this condition. Cool. So 93rd, what do you want to find? Friction coefficient, huh? So the uh, what thread starts slipping when this ratio is mu naught. So that will be natural log of mu naught. Oof, write it better way. That will be equal to pi times of k. Cool. So you have it. Friction coefficient is just k is equal to natural log of mu naught upon pi. Isn't this weird? Like these kind of numbers, natural, like these functions and numbers come out of nowhere from this problem. Why? Fine. You got this thing. And what was the second question? The acceleration of the masses when m2 upon m1 is bigger. Oh, sorry, it's equal to this thing, which is bigger than mu naught. Fine. Oh, so now it's not in stasis anymore. So you can only use this equation. Let me go. Uh-oh, no. Even this equation is wrong because there's acceleration over here. So instead, this is not dt. No, we got friction opposing the acceleration, right? You also got tension force, which may or may not oppose acceleration. So let's say m2 is bigger, so it's going down. Then this thing is slipping and okay, think which of these tensions must be bigger, T1 or T2? But I mean, the accelerations are the same, right? Yes, the accelerations are the same, of course. So then we just have T2, so like G minus T2 upon M2 is equal to T1 upon M1 minus G or something. Then M2 is bigger than M1. This doesn't really tell anything about what's happening. Oh, come on. What is this? Seriously. So at least we can say, okay, this thing, both of these are just positive. So you will be able to say that M2G is more than T2. So T2 is less than M2G. Okay. And T1 is, it's bigger than M1G. Okay. How does this even help us? We already know. Like M2G is more than some certain, it's more than M1G. Yes. So this doesn't give us anything. What can we do? What can we do? We know why friction is acting. Yes. You know what? Let's go with the fact that you can use dt as to be. We can make dt to be negative as well. So then this is going. This element is it's going like this. You got dt pulling it up. Friction opposing the motion, right? Yeah, exactly. So then this will be, and then it is accelerating in fact. So it's like dt minus, so this thing, where did it go? Oh, come on, where did it go? Where's that differential equation? This. Oh yeah, so dt is equal to kt d theta, but that's what we said, right? So now it will be minus kt d theta is equal to dA times m. Sorry, a times dm. Yes. So what's dm? It's just gonna be m upon. Oh no. That doesn't make any sense. Of course, okay, now I understand what went wrong. This is massless. The string is massless, so okay, acceleration does not play a role for this string, so it's still the same thing. Cool. So you can still use this equation, right? It's just that we don't know what T2 and T1 are. Oh, come on. So pi k is equal to natural log of mu naught, right? So you can write, okay, natural log of T2 upon natural log of, yeah, upon T1, sorry. That should be equal to natural log of mu naught. So you can say, okay, T2 is this many times T1. Once you have this, everything else is solvable now. So you'll still need that equation. What's this? Okay, cool. This looks good. Yeah, it looks good, I guess. So the dm thing was 0. That's the main thing that we did. Okay, now let's try to solve this. So from here, T2 upon M2 plus T1 upon M1 is equal to 2G. And you got this equation, so you can figure out what T1 is. It's such a long day. And then you have to figure out the acceleration. Why? Okay, do it. So T1 and what will this be? T2 is just mu naught times that. Sorry, eta naught. So eta naught M1 plus M2 upon M1 M2 is equal to 2G. Wait, you are saying M2 upon M1 is eta and weird. Fine, we'll take that. And then this just becomes T1 upon M1. So because this is only, and this will be this cancels, so just got, maybe I should just use M2 over there. Yeah, it will be better. So T1 upon M, no, okay, the T2 upon M2 is what we would have needed. So upon M1 is better. U naught, and you got M2 upon M1 is the eta naught. Yeah, so it's like this thing upon eta plus 1, exactly. Perfect. Is equal to 2G. So once we have this, you can figure out what this acceleration should be. So this upon yeah, like 2 upon this. So what will this be? G times of 2 upon, well, okay, write it in a better format. 2 eta upon eta naught plus eta. Okay, and then minus 1. Looks good. Yes, this is how it should be. Perfect. Yes. So then this is just t times of, this will cancel, eta minus eta naught upon eta plus eta naught. Wow. Just wow. This is awesome, isn't it? Usually I don't feel so fascinated about these kind of questions, but look at this. Just what is this? How did this kind of thing come out of such a basic question? Fine. 94th. A particle of mass m moves along the internal smooth surface of a vertical cylinder of radius capital R. A vertical cylinder of radius capital R. Find the force on the smooth surface. Find the force with which the particle acts on the cylinder wall if at the initial moment of the time its velocity is v0, forms angle alpha with horizontal. So it's a vertical cylinder. So like, wait, what? Vertical face of, sorry, wait, smooth surface. Oh, it's surface. Sorry, not face. So smooth surface of a vertical cylinder. So by vertical you mean like standing up. Okay, so some cylinder like that. This particle is moving on it. Yeah, along the internal surface. So like this, spiraling down. Okay, find the force with which the particle acts on the cylinder wall if at the initial moment of the time its velocity is v0 and forms an angle alpha with the horizontal. What? Wait. What? So say the particle is on the behind wall, right? So the wall behind us. Then this is going like this, I guess. So alpha with the horizontal, it's going down, I think. Or is it going up? We can't be sure. Initial moment of time, its velocity is v0. Okay, and it makes an angle alpha with the horizontal. Okay, so something like that, I think. Fine. So basically this is like v0 cosine alpha. That's this velocity, And hey, isn't this like, oh yeah, sure. Okay, okay, this is a problematic thing. So normal force is acting uh, out. Okay, this is hard to imagine as well. Sorry. How do we do this? Uh, Down as well, and it's not pure rotation. Are we sure that formulas that we use will apply in this case? I mean, they must. Otherwise, how do we solve this? Uh, think about it. If this is just going like that, that velocity is in fact not restricted at all, right? It cannot change the right. The normal force cannot change this kind of velocity that is perpendicular to it. Actually, it can, because uh, it obviously can. I mean, like, it does change the direction of time. So why not? Why not this being changed as well? There's gravity acting on it, which changes this, sure. But are we sure the normal force does not interfere with this? Uh, this is very weird. One thing we know is the normal force has no, what do we call it, z component at any moment. It has no z component, it only has an xy component. So the z velocity is not changing because of the normal force, it's only changing because of the gravity. That's one thing we know for sure. The xy component though, well, those are dependent on normal force. And how does it depend? That equation we don't know. We don't know that equation. One thing we know is like this particle is going. Hmm. Wait, if there's oh wait, we could do that. We could do that. What we'll do is that we'll just drop a stone, so something, uh, in from the center of the cylinder, and it will, yeah, it's like this being dropped and this being set free. Both will happen simultaneously, and then we'll take the point of view of this stone. Right. But will the forces also? Yeah, it does. It always works like that. Acceleration, we can go from here to here, right? We can do that freely because we know how to do it. Yes, so we'll just do that. We'll drop a stone and then we'll take the point of view of that stone. There's the pseudo force mg acting on this guy. So that means it's basically just not doing anything like that. And oh, now I understand what's happening exactly. So this is like if you imagine this particle on, let's say, a very light ring, which is also sliding down, right? It's always on that imaginary light ring. Then you might think, okay, the center of this ring. So yeah, like center of mass and stuff. So translation plus rotation basically, but just a very weird way to present it. So usually we deal with it like that, right? So it's translating in the plane, in one plane, and in the same plane it's also rotating. So yeah, and in this case it's translating in one plane and rotating in some other plane. Still, it's just that nothing much is happening. So we can still do this, right? Of course. So first of all, it's this guy's z component. That will just be equal to. Oh, and what do we actually look for? We are looking for force with which the particle acts on the cylindrical wall. So yeah, fine. We just figure out what the acceleration of this particle with respect to this center of mass thing is. I know it's not a ring, so it's not center of mass, but you can still do it, right? So just some imaginary particle that's going with g downward. So what will that be? That will just be this component of velocity, which is not changing, by the way, because no work is being done in those degrees of freedom. Oh, come on. Don't take that into your... Uh, but yeah, it's not changing. That's all I can say. Right? Of course. Ah, how do I say this? The the XYZ kinetic energies, they are only dependent on the forces of the XYZ at directions. So when I say this, what I mean is that changing y, so changing kinetic energy in y won't necessarily change the kinetic energy in x. So that's what I'm saying, that gravity changes the z component of kinetic, I mean the z component of kinetic energy, and the xy component, that is not changed because normal force does no work. So we would expect this to be going with the same velocity in the xy component. So the same speed, sorry. So you will just have v naught cosine theta square, that upon this guy's radius, right? That would be our acceleration. So that in this direction, like the r hat, small r hat, fine. Yeah. So that is exactly this times m, sorry. So this thing times m, that's exactly what we're looking for, the normal force. No problem. Really, it's no problem at all, right? And the other part, we don't care about it because gravity takes care of that. And yes, that's how it should be. Yeah, because gravity cannot change the xy components. Yes. So what am I saying? First of all, the acceleration is just v naught squared c squared upon r in the radial direction as viewed from this point, but then actually it's just that acceleration plus this acceleration. But of course, this acceleration cannot be achieved by normal force, and this acceleration cannot be achieved by gravity. So from that decomposition, you can say like this thing is just normal force upon mass, and this thing is the gravity force upon mass. So G basically. Cool. That does it. I know it sounds very technical, but sometimes it does happen that your equations don't work in cases where you might expect it to work. So it's better to be safe than take the risk and just say this is how it should be. So you got it. mv naught squared c squared upon r. That's the that's normal force. Oh, c squared is cosine squared alpha, right? And yeah, that cosine squared alpha thing is only for the initial condition, right? So alpha changes with time, but the xy speed remains same. So nice. Let's go to 95th. Find the magnitude and direction of force acting on the particle of mass m during its motion on the plane xy according to law x is equal to a sine omega t. Oof. So it's on an ellipse basically. And now find the magnitude and direction of the force acting on the particle. Hey, okay, this is actually parameterized already, so you don't have to worry about that. Wait, is this for real? Are you saying that's it? Nothing else? Ah, this is easier than I expected it to be. Fine, so just do it. A sine omega t and then b cosine omega t, and we just differentiate this to get the velocity. Yes, so you just need to find the force. That's it. Huh? Well, what's the velocity going to be? It's going to be omega out, a cosine of omega t, then negative b sine of omega t, that stuff. Then differentiate once again, like omega squared, negative omega squared a. Wait a sec. Looks like the ellipse also has v squared upon r thing happening. Oh wow, this is unexpected. Huh. Yeah, I mean this really is unexpected. Okay, so you got. Huh. Fine. Let's do it. So sine omega t. Then you got b cosine of omega t. So these constants still remain like that. Nothing was added or so. I mean, yeah, it wasn't changed. It's still collinear with r vector. So, man, this is a weird fact. Like a vector is still negative omega squared r vector. How did this happen? I have no idea. So for ellipses as well, you can just do negative omega square r vector, and that will give us the acceleration. No, okay, this only happens when your eccentric angle is varying linearly with time, right? Of course. Uh, I mean, it's not exactly eccentric angle, but you get the idea. So it's on an ellipse and its phase or whatever that's changing linearly with time, and then you can still write a is equal to negative omega square r. It's not that it's moving with constant speed on the ellipse. No, just that it's okay. It's like some kind of projection or something. So if this was a circle, this was the auxiliary circle of this ellipse, right? Then I don't know. This might be the thing. This is the ellipse. This is the auxiliary circle. This is moving like that. The acceleration is pointing in this direction and whatever. So yeah, like negative omega squared. Sorry. Yeah, omega is the same exactly. R vector is in this direction and acceleration is also in this direction. Now, when you start squishing it basically to this ellipse, it still remains like that. So yeah, now R is over here. So R vector is in this direction, and then omega is sorry, acceleration is still in this direction. Very weird. Whatever. We got it. Now, what do we want to do with it? Find the magnitude and direction. We just got it, right? So, yeah. Of the force. So the force is negative m omega square r vector that we did. And the magnitude of the force is just m omega squared. And the magnitude of r vector, yeah, whatever that was at that moment. So square root of a squared sine squared of omega t plus b squared cosine squared of omega t. So it changes with time. 96th. Body of mass m is thrown at an angle to the horizontal with the initial velocity v naught. Assume the air drag to be negligible. Find. Mass m is thrown at an angle to the horizontal with initial velocity v naught. Huh? Mass m is thrown at an angle to the horizontal. Okay. Instead of mass m, assuming the air drag to the momentum increment that the body acquires over the first t-second of the motion. I mean, there's only gravity acting on it. What are we even talking about? The modulus of the momentum increment delta p during the total time of the motion. So for that you will need a time period. Sorry, the time of flight. What am I saying? Time of flight. So a is no big deal. It's just gravity acting on it. That's why this momentum change will be mgt in the downward direction. Now, how do I say what downward direction will be? I'll just say negative j hat. And what about b? So for b, you will need what the time actually is. So t is equal to 2 uy upon g. So in this case, uy is v naught sine alpha. Wait, do we have it? We don't have an angle, do we? Oh, wait, what? We don't have an angle? But then how am I supposed to write this? Models of the momentum increment during the total time of the motion. I'm not so sure what we are supposed to do. Increment. Okay. Okay. The momentum as a number. I mean, the magnitude of the momentum that doesn't change. Yes, but this vector does change, and it relies on sine alpha. So without that, I don't know how to give you the answer. At an angle, what? What? It's not working. Fine. The time required is just 2v naught sine alpha upon g. So then the momentum change in that amount is just negative mg times this time. So negative 2mv naught sine alpha times j hat. I don't like using this alpha that has not been yet defined. 96, 97. Let's go. Ah. At the moment t equal to 0, stationary particle of mass m experiences a time-dependent force where a is a constant vector, tau is the time during which the given force acts. Find momentum of the particle when the action of the force discontinued. Oh, so they just give us the force. Fine. And a stationary particle. So t equal to 0, it's stationary, and then it expresses its force. Fine. So basically, just gave us what uh, the acceleration is. Okay. A is a constant vector. T is a time during which the given force acts. Okay. Find the momentum of the particle when the action of the force is continued. Hey, so like it's along one direction only. That's what you're saying, huh? Oh, so uh, it's constant vector. We just talk about the magnitude of A as A. So the thing is, the acceleration called W. That will be this things A upon M T into tau minus T. And from here you can figure out what velocity should be and everything basically. Right? I'm just integrate it with a simple time, get velocity, and then so time once again, and then you get position. Momentum of the particle when the action of the force discontinued. Oh, oh, so this is the time during which the force acts. Uh-huh. First of all, just find the velocity. Integration with this thing, right? So A upon M, you got tau times T, so like tau times T squared upon 2 minus TQ upon 3, and initially it's 0 anyway, so there no constant involved in there. You got the velocity. Now, momentum change of the particle, so like mv. This guy's changed. Where you go? When the force discontinued. So basically at t equal to tau, what was momentum? Because initially it was 0. That's it. What kind of question is this? So A, it's just, yeah, like, what will this be? 8 tau cubed, and then you got 1 upon 2 minus 1 upon 3, I guess, like 1 upon 6. So 8 tau cubed upon 6. It should do it. Oh, in fact, it should be A vector tau cubed upon 6 because, yeah, there's always that thing. In fact, over here as well, I should actually use vector form. Okay, cool. And then what? B is the distance covered by the particle while the force acted. So we can integrate this once again. Just have the x vector as, oof, it's gonna be really bad. Ah, this is really bad. Okay, do it. Just do it. We just have to do it. So a vector upon m, and then you of this thing. So tau t cube upon 6 minus t power 4 upon 12. So when you put tau in there, or first of all, just simplify this thing like a vector upon m, t cube upon 12 into 2 tau t minus, sorry, it's t cube out, so it should be just 2 tau minus t. That should do it. So when t is equal to tau, this just becomes tau, this becomes tau, and this is just 12. So yeah, this will just be equal to a vector tau power 4, I guess, upon 12m. That's the distance traveled, I guess. Yeah, I mean this force is always in the positive direction, positive a vector direction. It's never negative. So throughout that time, it was definitely just going in one direction. It's not going back. So displacement is the same thing as distance in this case. 98. At the moment t is equal to 0, a particle of mass small m starts moving to a force. This force where f and omega are constants. Find the distance covered by the particle as a function of t. Draw the approximate plot of this function. So force is given, we want to find the distance covered by the particle as a function of t. Fine. So you can just say, okay, acceleration is like a naught times, uh, I should probably use f naught upon m, whatever, sine of omega t, and then just gonna integrate that. So that will give us the velocity as, doesn't it look like SHM? Yes, it does. Anyway, so integration of this thing is going to be negative cosine omega t and that upon omega. So negative f naught upon m omega cosine of omega t. And then once it integrates, like x will be, initially it's 0, right? Starts moving. Exactly. So it's 0 at that point. Cool. And then integrate it once again. So sine negative f naught upon m omega squared sine of omega t. I should do it. What do you want to find? You want to find how long. Wait, that's 99. Sorry. Oh, so both of these have the same kind of thing. Okay. Find the distance covered by the particle as a function of t. You got it. Draw the approximate plot of. Wait, what? You mean the distance covered? Are you serious? Oh no. Distance covered, huh? You got the displacement, but they want the distance. This will only work till some certain t values. So, what do we do now? Oh, come on, think about it. Oh no, this is really bad. This isn't nice. This isn't nice. You know that distance never decreases. So this will be really bad because, oh no, sine omega t. Oh, okay, it's going to increase till you have omega t is equal to pi upon 2, and then it's going to decrease. So till pi upon 2 it matches up, but then after that things start getting problematic. So instead of the decrease, you need to inverse that basically. So a graph speaks much better. You can't find it as a function of time directly, but do something else. Okay, so once you know what v is, we could just take the mod of that guy, right? So then this will just be, so speed basically, that's just this. Huh. Okay. And what then? So how do we integrate this? I have no idea. But even an integral definition is still a function, right? So I guess this will work, integration from 0 to t of cosine omega t, whatever that is supposed to be, mod and everything. I know that function is like continuous, it's smooth, it's everything, but what elementary function even resembles that? We don't know. Because it relies on the previous knowledge of what happened, and that's why this function is hard to write down. Something I can do about it. Well, I should just leave it like that, huh? Sorry, it's supposed to be x. Right? So the distance traveled, you got as a function of time, but a very badly defined functions. You got this. Now let's try to graph this. First of all, I just graph displacement. So this is omega t axis, and this is d. Fine. Okay, not d. It should be x first. So displacement is like this. I mean, okay, it's supposed to be in that negative f naught direction, but yeah, let's just say, yeah, okay, whatever. Let's multiply this by negative f naught hat dot x vector. That should be doing it. That's our displacement. So now this thing is a sine curve kind of. Cool. So for displace, sorry, for distance, this will be this, and then it will be this. So yeah, just look at this. Till 3 pi upon 2, it will just keep on increasing, and you get the idea. It just keeps on increasing basically. So should I draw a graph for this? No, no need to do that. Still, not draw it. So we got distance over here, time over here. Yeah, whatever, something like that. 99. 99 is at the moment t is equal to 0 particle first. Okay, similar kind of question. How long will it keep moving? Okay, will it be moving until it stops for the first time? What distance will it traverse during that time? What is the maximum velocity of the particle over the distance? Hmm. Uh, so it's an SHM thing, right? Yeah. Okay. I want to do everything once again. It's gonna be complicated to do that. At this point, we know how to do it. It will just be equal to the displacement is basically like f naught upon m omega squared negative and then cosine of omega t, right? Just how we did it previously. Now, same thing, just fast forward. So once you have this displacement, right? How long will it be moving? So what's the velocity? Velocity will just be f naught upon m omega sine omega t negative, sorry. So it will keep moving till what? So at t is equal to 0, it's at rest and then it keeps on moving. Eventually you reach t is equal to pi, so omega t is equal to pi, and at that moment it will stop, right? And then what? So how long? Just omega t is equal to pi. So t is equal to pi upon omega. That's when this will stop. It's 99th. Just use capital T. Pi upon omega. Okay, what else do you want? What distance will it traverse during that time? So the displacement is this thing. So I keep on going. Oof. The distance travel, that's kind of initially it's at 0, right? So it's at an extreme position basically, and then it will just, so yeah, till the other extreme position. So it will be all of the displacement in between. Yeah, that's, so initially at omega t equal to 0, your x is just negative f naught upon omega squared. And finally at omega t is equal to pi, this will be f naught upon omega squared. So you can guess what it's going to be. The distance is just 2f naught upon m omega squared. That does it. And last question is, what is the maximum velocity of the particle over this? I mean, it passes through the mean value, the mean equilibrium point as well. And that means the amplitude will also be there for 1 second, right? For a moment. So yeah, there you go. P max is equal to f naught upon m omega. Next, 100. A motorboat of mass m moves. Oof, it's a long question. 3-part. Moves along a lake with velocity v naught at t equal to 0. The engine of the boat is shut down, assuming the resistance of the water to be proportional to the velocity of the boat. X is equal to negative rv. First of all, start doing something about it. So we've got acceleration vector is just negative r upon m v vector, right? So now what do we do with it? How long the motorboat moved with the shutdown engine? So time dependence. Okay. I mean, since it's all in just one direction. Hey, okay, it's negative rv. It's not negative rx. If it was negative rx, it would have been different. Okay. How long the motorboat moved with shutdown engine? uh, it's all just happening in one line, right? Yes. So yeah, we can just get rid of these vectors. Okay, what is this numbers? So then a upon v over there, and then a is just dv upon dt. So it's like dv upon v is equal to negative r upon, just like the first order kinetic thing. Okay, dt. So then that just becomes, yeah, like uh, natural log of v. So it starts at, okay, it starts at v naught. All right, fine. I understand what's happening. So it starts off at v naught. It's like natural log of something like nuclear decay or something, whatever. V upon v naught is equal to negative r upon m times t. So you can say, okay, the velocity is v naught e power negative r t upon m. Once you got this, you can add back the vectors. How long the motorboat moved with the shutdown engine? Infinity. Yeah, really, infinity. Till infinity. It just keeps on moving. Okay, because you asked how long, not till what distance did it move. Okay, velocity of motorboat. So strike A is infinity. Okay, cool. What about B? The velocity of the motorboat as a function of distance covered with the shutdown engine, as well as the total distance covered till the time stop, as well as the total distance covered till the complete stop. Nice. So second part is something that we can do. All right. You got what velocity is. Just integrate this and you will get the position. Yes. So integrating this thing, just get x vector is equal to v naught vector e power negative rt upon m, and then you divide by negative r upon m. So this will be negative m upon r and so what's happening to this negative m upon r. And now this goes from 0 to x, and this thing, it goes from 0 to t, right? So just got x vector is equal to, so at 0, this thing is just 1, like e power, all that stuff, right? And this one's going to be m upon r v naught vector, and then you got 1 minus e power of negative rt upon m. So as t approaches infinity, our x vector basically just approaches m upon r. And what we actually want is the velocity of the motorboat as a function of the distance covered, right? So from here, you want to write v vector. Where did it go? This thing. Cool. So you can write x vector is equal to m v naught vector upon r minus, so m upon r, and then you got this thing v naught vector e power, all that stuff. So that's just v vector. So you can say, okay, multiply by r upon m. So v vector is equal to v naught vector minus r upon m. Wait, what was r, by the way? Oh yeah, this constant. Fine. R upon m times x vector. This is the other equation that we need. So equation, and first equation that we need is x maximum, right? That is just yeah, mv naught vector upon r. Cool. So this is done. Let's go to C now. The mean velocity of the motorboat over the time interval beginning with the moment t is equal to 0, during which its velocity decreases, wait, what? These many times. Oh, so from v naught to eta v naught, right? Till that, what is the mean velocity of this thing? Fine. So once, oh yeah, you can just use this relation and get it. No, you can find what x is, yes, but what t is, you also need that. Fine, at least we know what this thing is. So it's just natural log of eta. Uh, yeah, it became, wait, where did it go? decreases these many times, right? So it's going to be v naught upon eta. That's what we will do. So this is equal to r upon m times t. So m upon r times that. Okay, and what's the x at that point? So using this equation, you can just say your x will just be equal to m. Sorry. Yeah. So v naught vector minus, or you could just use this thing. Nah. So v minus v naught, which is just v naught into 1 upon eta minus 1, and now divide by that. So it's got x upon t is equal to this upon m upon r natural log of eta. Cancels perfect. So it's got the average velocity is v naught into 1 minus eta upon eta natural log eta. This should be the thing. So we got C done as well. Is this correct? Guess so. Yeah, whatever. So C is the average velocity in that amount of time. So it's not write it like that. I might mistake it for the general expression later on. So the thing is, it's just v naught into 1 minus eta upon eta natural log of eta. Next question. Hey, actually, you know what? No, let's stop here because 100 questions. Nice number. So I'll see you guys in the next video.